You've probably seen this a million times without even realizing it. Think about an old newspaper photo, or maybe an image on a really old school computer screen. Ever wonder how they managed to get all those shades of gray when they could only print, like, black dots? Well, it's all a clever visual illusion, a trick that's actually still super important in digital imaging today. And this really gets to the heart of the problem we're talking about. I mean, think about it. Your average digital photo has millions of colors. But what do you do when you have to show that amazing, colorful picture on a screen that can only handle, say, black and white? That's it, just two colors. You have to throw away a massive amount of information. So, how do you do it without turning the image into a complete mess? Well, the most obvious, kind of lazy way to do it is to just go pixel by pixel and make a simple choice. Is this pixel more black or more white? Whichever it's closer to, that's what it becomes. This is called thresholding, and, well, the result is exactly what you'd expect. It's a harsh, blotchy mess. You lose all the smooth transitions, all the nice details. It's just bad. Thankfully, there's a much smarter way to do this. It's called dithering. And here's the magic. Instead of just chucking all that color information in the trash, dithering takes the few colors you do have, like black and white, and arranges them in these really clever patterns. It's so clever, in fact, that it tricks your brain into seeing all the shades and tones in between. They're not actually there, but your eyes and brain fill in the gaps. It's a total optical illusion. And the hero of our story today, the algorithm that pulls off this amazing trick, is called the Floyd-Steinberg dithering algorithm. It's one of the most famous ones out there, and for good reason. It's so simple, yet it's incredibly powerful. It lets you create these amazing-looking images with a tiny, tiny color palette. So let's dive in and see exactly how this thing works its magic. Okay, so the first thing you need to know is how the algorithm travels across the image. It's super methodical. It starts at the top left corner and works its way across pixel by pixel. When it hits the end of a row, it just jumps down to the next one and does the same thing, left to right, top to bottom. To really get how this all comes together to make a great image, we've got to zoom in and follow the journey of just one single pixel. For every single pixel it lands on, the algorithm follows a simple three-step recipe. First, it quantizes the color. We'll get to what that means. Second, it calculates something called the quantization error. And third, it updates the pixel with its new simplified color. Now, steps 1 and 3 are pretty straightforward. But step 2, calculating that error, that's where the real secret sauce is. All right, let's tackle step 1, quantization. Don't let the fancy word scare you. It really just means making a decision. The algorithm looks at the original color of the pixel and forces it to become the closest color available in our super limited palette. So for us, that means every single pixel is going to become either pure black or pure white. That's it. Let's walk through a real example. Imagine we have a single gray pixel. On a scale where 0 is pure black and 255 is pure white, let's say this pixel has a value of 100. The algorithm's rule is simple, right? Anything below the midpoint becomes black. So our pixel with a value of 100 is forced to become pure black, which has a value of 0. Okay, so here's where it gets really interesting. The pixel was 100, and now it's 0. That means we have a difference, a leftover bit of information, of 100, right? That's our quantization error. Now, the simple, naive approach would just throw that number away. But Floyd-Steinberg, it does something absolutely brilliant with it. Because see, the secret to this whole thing, it isn't actually about what you do to the pixel you're working on right now. That's just a simple rounding decision. Easy stuff. The real genius is what you do with that leftover error. And this gets us to the absolute core of the algorithm, a concept called error diffusion. Think of it like this. The mistake, that little bit of error we calculated, isn't forgotten. It gets passed on or diffused to the neighboring pixels. So one pixel's mistake actually helps its neighbors make a better decision. Now, this isn't just a random spray of leftover value. No, it's very, very specific. This little diagram shows you exactly how it works. That X in the middle, that's our pixel, the one we just changed. And the numbers around it show how its error gets split up and handed off to its neighbors, but only the neighbors the algorithm hasn't gotten to yet. So that error we calculated gets chopped up into 4 pieces. The pixel immediately to the right gets the biggest chunk, 7/16 of it. Then the rest is distributed to the 3 pixels in the next row down. 3/16 to the one on the left, 5/16 to the one directly below, and a tiny 1/16 to the one on the right. See how it's pushing the error forward and down? It's always moving in the same direction the algorithm is scanning. And this is the crucial part. This error isn't just sitting there. It gets added to the original color values of those neighboring pixels before the algorithm even looks at them. So when we get to the very next pixel, we're not starting from its original color. We're starting from its original color plus all the leftover error it just inherited. It creates this amazing chain reaction that ripples across the entire image. So, what happens when you take this really simple pixel by pixel process and just let it run thousands, maybe millions of times across an entire image? Well, you get to see how all those tiny little decisions add up. It's time to see the final result. And here it is. The difference is just night and day, isn't it? On the left, that's the simple thresholding method where we just threw the error away. It's blocky, it's harsh, all the detail is gone. But on the right, that's Voigt-Steinberg. Because it's so cleverly managed and passed on that error, it preserves so much detail and texture. It creates that beautiful, smooth illusion of tones that aren't even there. So let's wrap this up. What are the big things to remember? First, dithering is basically a magic trick for your eyes. It creates the illusion of more colors. Second, the whole process happens in order, one pixel after another, and each one affects its neighbors down the line. And most importantly, the secret, the absolute key to the whole thing, is to spread the error, not throw it away. Really, the Floyd-Steinberg algorithm is just such a perfect example of a beautiful, elegant solution to a really tricky problem. It's a great reminder that sometimes the best answers aren't more complicated. They're just clever tricks that play on how we humans see the world. And it really makes you think, doesn't it? What other clever, invisible illusions are powering our digital world every single day?